you, Chris. So first, just thank you all for coming here, and I'd like to also thank the organizer for the invitation. Right, so one of the motivations for my talk is coming from study of a p-Adic Fourier transform, and I will begin with quickly reviewing this Fourier transform and how some properties of it are related to invariant norms. And then as the Fourier transform is intimately connected to the Heisenberg group and its representation theory, I will also quickly review these two. And at the end, after talking about some results, I will end with some open questions. As usual in p-Adic analysis, p-Adic numbers are going to play two roles in our talk. The first role is the topological group on which we will do analysis, and the second role is as the field of coefficients. So most functions that are going to appear in this talk are going to be from the p-Adic numbers into some p-Adic field, mostly CP, and vector spaces are going to be over CP as well. But I begin with a slightly more general setup. Let's work with an abstract field of coefficients, which is algebraically closed and of characteristic 0, and later on we'll spatialize it to the case of the complex numbers and later on to CP. We'll work with the space of Schwarz functions, those functions from QP to C, which are locally constant and compactly supported. And here the point is that since QP is topologically, well, it is locally compact and totally disconnected, there are many such functions. This is an infinite dimensional vector space over C. We choose a non-trivial smooth character of the additive group of QP. Smooth here just means that its kernel is open. And we define the Fourier transform of a Schwarz function f by the usual formula of integration against the character. And here what integration means is that if we look at the space of linear functionals on the space of the Schwarz functions, there is a unique one up to a constant linear functional, which is invariant under translations. I call it here the Haar functional, or sometimes it's known as the Haar distribution. And I just took here one normalization of it. And the Fourier transform of a Schwarz function is again a Schwarz function. So it's a linear operator on the space of Schwarz functions. This Fourier transform satisfies several of the usual properties that Fourier transform satisfies. It is almost an involution in this sense here. And I mean, if the kernel of psi of our character is not ZP, then there should be some normalization constant here. But in any case, the Fourier transform is a linear isomorphism on the space of Schwarz functions. And a property that will become very important later is the fact that the Fourier transform swaps translations and multiplication by smooth characters. So each function of this form is a smooth character, and it's also well known that any smooth character is of this form. And that specializes to the case where the field of coefficients is the complex number. So in this case, the Haar functional from before is now a Haar measure. We have the standard unit, the standard inner product defined by integration on the space of Schwarz functions. And the Fourier transform is unitary for this inner product. So it extends to an isometric isomorphism of the L2 completion. And I'd like to mention that it has the property, this inner product, that it is invariant under translations and multiplication by smooth characters. And also it is defined by this property in the sense that it is the unique inner product with this property up to a constant. And this is going to be one of the properties that we're going to consider when we later talk about norms. Okay, and now, and for the rest of this talk, I specialize to the case where the field of coefficients is CP, and I will omit the notation of CP from the field of coefficients. Right, so in this case, there is no notion of an inner product with values in CP. There is no notion of positivity in CP. And so our next best thing is to take the sup norm, right? We don't have L2 theory. And I will denote by C0 the completion of the space of Schwarz functions with respect to the sup norm. This is the space of continuous functions on QP valued in CP, which goes to 0 at infinity. But now we have the very strange behavior. The Hall functional now is not continuous. It does not extend to continuous functions, not ones with compact support. And the reason is that it is not bounded on subsets of a compact set. So for example, here the sequence of characteristic functions are characteristic functions of smaller and smaller sets inside ZP, and yet their integral is the sequence of numbers which is unbounded in CP. And as a consequence, the Fourier transform is also not continuous with respect to the sup norm, and we can take the same example to see this, right? If we take these characteristic functions, it's an easy computation to compute their Fourier transform, and you can see that the sup norm is 1. Of course, they are characteristic functions, but the sup norm of their Fourier transform, you can make it as small or large as you wish. Okay, I'd like to mention two results about the bad behavior of the p-Adic Fourier transform. So the first result is from the 1970s. It was proved independently by Fresnel, de Matan, and Amis and Escasou. And it says the following: if you consider the subspace of the space of Schwarz functions, of those functions which are constant on cosets of ZP, right? This is this space here. The Fourier transform of such a Schwarz function is a Schwarz function supported on ZP, and therefore we have this map here. And on this space, the Fourier transform is continuous and extends to a map between the completions. And unlike what we are used to about Fourier transform, this extension is not injective. And I would mention that Fresnel and de Matan also show that it is surjective. The second result is with the Shalit. Now going back to the case, considering the Fourier transform on the entire space of Schwarz functions, we consider the question of how this continues it in the following sense. We consider its graph and ask what is the closure of this graph. And it turns out that in this sense, the Fourier transform is as discontinuous as it can get, because the closure is everything. In other words, if you take any two functions in the space C0 and any degree of precision, you can find a Schwarz function f, which is a very good approximation of G1, while at the same time its Fourier transform is a very good approximation of G2. Okay, we can reformulate the last theorem about the discontinuity of the Fourier transform in terms of invariant norms, or in terms of norms. Let me denote by this wedge, norm with a wedge, the Fourier norm. This is the norm that you get by composing the sup norm with the Fourier transform. Now, the fact that the Fourier transform is not continuous with respect to the sup norm is basically equivalent to saying that the sup norm and the Fourier norm are not equivalent norms. But the discontinuity theorem is equivalent to a much stronger statement that these two norms are so different than each other that there exists no semi-norm in the space of Schwarz functions, which is smaller than both of them. And I think about this property as some kind of independence of these two norms. And until now, we didn't consider it, but it will become important from now on to know that these two norms are invariant under translations and multiplication by smooth characters. And I would like to mention several points about this work, maybe something to keep in mind during this talk. Actually, okay, the first one, I'm not going to talk about it, but I just wanted to remark that at the beginning, when we proved the theorem about the discontinuity of the Fourier transform, it was unrelated to the non-injectivity result from the 1970s. But now these two results are both implied by the same main result that we have. And the second thing to keep in mind is the following. I mean, maybe as some kind of substitution to the L2 theory, we would like some kind of, and we can prove some kind of a rigidity result for the subnorm similar to the uniqueness of invariant unitary structure on the space of Schwarz function when we consider the case of the complex numbers. I mean, we cannot hope for uniqueness like we had over the complex numbers, because we know the subnorm and the Fourier norm are two different invariant norms. But yet we can still say something about in the spirit. And the second point on which we have only partial results is some kind perhaps of a classification of invariant norms on the space of Schwarz functions. So are there any questions until now? Okay, so let me tell you what we're going to do next. Our next goal is, well, it serves also as a generalization of the construction of the Fourier norm and the results at the Fourier transform and the results about this Fourier transform. And also about this second point here about classification of norms, we are going to construct a family of invariant norms by using a family of special operators, intertwining operators. The Fourier transform is just one of them. And the way that we're going to construct this family is using the Heisenberg group and its representation theory. So let me recall this. Okay, we'll work in a slightly more general context, considering also higher dimensional Heisenberg groups and Fourier transforms. So let's fix a positive integer d. We will construct the Heisenberg group from the symplectic space. The standard 2D-dimensional symplectic space is this space here. This is it's a vector space, and omega is the standard symplectic form given by this formula right here. Then the Heisenberg group attached to it, which I do not like this, its underlying set, well, it's the vector space of the symplectic space product with the QP, and multiplication is given by this rule here. So an element here is a pair where W1 here is an element in the symplectic space. It's a vector in a 2D dimensional space, and T is a number in QP. And what you can see in the formula, so in the first component, we're just adding vectors. In the second component, we're adding these two numbers, but with some twist coming from the symplectic structure, which makes it non-commutative. But it is almost commutative. This is a two-step nilpotent group. and its center consists of those elements of the form 0t. It inherits its topology from QP, and it makes it a totally disconnected and locally compact topological group. Okay, we choose a smooth character, non-trivial one of the additive group of QP, and we will work with the space of Schwarz functions on QP to the D. Then the Schrodinger representation attached to the character psi, which I'll denote by rho psi, is a representation of the Heisenberg group on the space of Schwarz functions defined by this formula here. So here W is a pair A and B, each of them is a vector in QP to the D. And going from right to left, what you see here is first a translation of a function f, then a multiplication by a smooth character, and then this is just a constant. So essentially, the action of the Heisenberg group on the space of Schwarz functions is by translations and multiplication by smooth characters. Okay, whenever it will be convenient, I will omit the notation rho psi if it's obvious. The kind of representation theory that we are going to need is smooth representations. So let me just recall the definition. If you have a totally disconnected group G, totally disconnected topological group, and the representation V of it, we are saying that V is a smooth representation if each vector in V is fixed by an open subgroup of G. And then the main result, I mean, this all part is classical. The main result about the representation theory of the Heisenberg group, smooth representations, is the following. It's a smooth analog of the Stone von Neumann theorem. First, the Schrodinger representation rho psi that we just defined is smooth and irreducible. And second, any smooth and irreducible representation of the Heisenberg group. So for any smooth irreducible representation of the Heisenberg group, the center of the Heisenberg group acts via some smooth character. And if it has character psi, central character psi, it is isomorphic to the Schrodinger representation rho psi. And using this, we're going to construct the intertwining operators as follows. Okay, so we have an action, a right action of the symplectic group on the Heisenberg group as follows. If you take an element G in the symplectic group, it acts by multiplication on the right. So the convention here is that vectors are the row vectors, and then G acts from the right. And this action is a continuous automorphism of the Heisenberg group, which is the identity on the center of the Heisenberg group. Okay, so we can take this automorphism and define new representations as follows. I'll denote by rho psi G the new representation that you get by composing the Schrodinger representation with this action by G. Now, since G is an automorphism and continuous, this new representation is again smooth and irreducible. And since the action of G is the identity on the center, the new representation has the same central character psi. So now by the smooth Stone von Neumann theorem, the two representation, the Schrodinger and the new one, rho psi G, are isomorphic. So there exists a linear map on the space of Schwarz functions, which is an isomorphism between these two representations. Here I wrote explicitly what does it mean. And these operators are called intertwining operators, and by Schur's lemma are unique up to a scalar. Okay, I just remarked that this association of an intertwining operator is a projective representation of the symplectic group, but not a true, but we cannot make it a true representation. We cannot choose these intertwining operators in a compatible way so that they form a representation of the Heisenberg, of the symplectic group. Okay, and let me give you an example. So in the lowest dimension, when this one, this Heisenberg group can be realized as the group of matrices of this form. Then the two symplectic group of QP is just SL2QP. And the Fourier transform is an intertwining operator for this particular G. And how do you say it? Here I wrote the action of this G on the Heisenberg group. This is the automorphism it defines. And then to say that the Fourier transform is an intertwining operator for this G amounts to saying that this equality right here, which when you unwind the definitions, it's just saying that the Fourier transform swaps translations and multiplication by smooth characters. Okay, next, we use these intertwining operators to construct invariant norms on the space of Schwarz functions. And invariant norms are always, unless otherwise stated, are always going to be of the Heisenberg group. So if you have a norm, which is an invariant norm on the space of Schwarz functions, then composing it with an intertwining operator is again an invariant norm. And I attached here the computation that shows it. And therefore, we get the right action of the symplectic group on the homotopy classes of invariant norms. And what we will be interested in are these norms that you get by composing it with the sup norm. I mean, the reason is that to begin with, we don't have too many invariant norms that we know of on the space of Schwarz functions. And basically, the sup norm is almost the only one we know which is interesting to consider. Okay, so there is an explicit formula for these operators TG, and so it can be directly compute. You can directly compute and see that an intertwining operator TG fixes the homotopy class of the sup norm if and only if it belongs to this parabolic subgroup. It is called the Siegel parabolic subgroup of the symplectic group, and therefore the orbit of the homotopy class of the sup norm is in bijection with the right cosets of the Siegel parabolic, which is some Grassmannian in its own right. This explains why I call it GR, and I will call it the Grassmannian. The fact that it is Grassmannian is not going to play any role in this talk, but I do think it's worth mentioning that this family of norms that we are going to construct, and later on family of irreducible completions that we're going to consider, are parameterized by some nice geometric object. Anyway, eventually we would like to work with norms and not with homotopy classes of them. So we would just choose in each homotopy class a norm in some uniform way. So if we have alpha in the Grassmannian, a right coset by G, I'll denote by norm alpha the unique norm in the homotopy class of this norm, which is normalized on the characteristic function of Zp to the d. And there is nothing special in this characteristic function, it's just one normalization. Right. Okay, I'd mentioned that By definition, if we have two distinct elements in the Grassmannian, alpha and beta, then norm alpha and norm beta are not homothetic. But it's not hard to see that they are also not equivalent. And later on, we will see that they are satisfying this stronger notion, which I said it should be thought of an independence of norms. Okay. Okay, are there any questions? Okay, so let me give a quick summary. What we have, from now on, you can forget almost entirely. I mean, maybe perhaps except for the next slide, almost entirely about these intertwining operators. That we have a family of norms on the space of Schwarz functions denoted by norm alpha for alpha in a Grassmannian. Each is invariant under translations and multiplication by smooth characters. Okay, so in this slide, we do need to remember what are these intertwining operators. This is a generalization of the result about the discontinuity of the Fourier transform. And I remind that the discontinuity result said that the graph of the Fourier transform is dense in this Cartesian product, and we can generalize it to a finite number of intertwining operators. If you take G1 up to Gn elements in the symplectic group, each belongs to a distinct coset of P. And Tg1 up to Tgn, some corresponding intertwining operators, then this subset here, this generalized graph of them, is dense in the Cartesian product here on the right. Okay, next, I'd like to fix some notations and definitions. So I would say that a unitary Banach representation of a group G is a representation of the group G on a Banach space B together with some norm. All our Banach spaces are going to be over the field CP, such that this norm is G invariant. And in particular, the norm of a Banach space in this talk is part of the data. Okay, so given such a unitary Banach representation of a group G, as usual, we will say that the vector V in B is topologically cyclic if the sub-representation it generates is dense in B. And I will say that the vector V in B is strongly cyclic if, moreover, any element W in B can be written as a convergent sum like this, which means that these coefficients, all of them except for countably many maybe, are 0, and the non-zero ones converge to 0 in CP. And we said that the unitary Banach representation is strongly reducible if any non-zero vector is strongly cyclic. Right, so in particular, any strongly cyclic vector is topologically cyclic, and any strongly irreducible representation is topologically irreducible. Finally, let me fix some notation. I will denote the completion of the space of Schwarz functions with respect to a norm alpha simply by writing the norm alpha in subscript. Then we have a result about the reducibility of the completions. For alpha in the Grassmannian, the completion by norm alpha is a strongly reducible unitary Banach representation of the Heisenberg group. If we have alpha and beta distinct, then the completion by norm alpha is not isomorphic to the completion by norm beta. In these slides, all maps are going to be continuous maps, and equivariant under an action of the Heisenberg group. And this result is kind of some kind of rigidity result for the completions by this norm alpha. So if you have any unitary Banach representation of the Heisenberg group and a non-zero map T from the completion by norm alpha to B, then the image of T is necessarily closed in B, and T is an isometry onto its image, well, maybe up to some scaling the norm on B. If we have a map T in the other direction from B to the completion by norm alpha, again non-zero, then T is necessarily surjective and induces an isometry from the quotient to the completion by norm alpha. Again, you maybe need to scale the norm. Right, so in general, if we just know that this guy, this completion by norm alpha is, say, topologically reducible, it's not true that any such non-zero T must be surjective. It could be the case that it just have a dense image, but not surjective. And in general, even when it is surjective, and it then induces an isomorphism of Banach spaces between the quotient here, but this isomorphism is in general not an isometry. And so let me give, maybe rephrase it or give some corollary from it in the simplest case. So in the case where D is 1 and norm alpha is just a sup norm, then the completion by the sup norm is the space C0, and the previous result tells us that this space is strongly reducible representation of the Heisenberg group. And if B is some unitary Banach representation of the Heisenberg group, and let's assume topologically reducible, then if you either have a non-zero map from B to C0QP, or in the other direction, then B is necessarily, again, up to scaling the norm, isometrically isomorphic to the Banach representation C0 of QP. Are there any questions? Okay. Okay, now we get, yes.
I have a question, Bertin Dira. If the restrictions of the if you take the coefficient of the Heisenberg group in ZP, you have a subgroup which is a compact subgroups, and I think a maximal compact subgroups. What happens when you consider your restriction to these subgroups, these compact subgroups?
Okay, so we can say some results about it now, but maybe so I mean there are several different setups, okay, to this question. So for example, in our case, it will be interesting to consider the representation on the continuous functions on ZP, representation under translations, and multiplication by the smooth characters of ZP. Okay, now
it is trivial.
Hmm?
The restriction is trivial.
Then
the restriction of your representation to the Heisenberg group with coefficient in ZP.
Well, so again, so if we just restrict this, I mean, if we just restrict this representation to where the coefficients are in ZP, when, I mean, it depends on what character you begin with, but if its kernel is exactly ZP, then it's a trivial action. So I think that the more interesting question is, again, to consider the action by translations and multiplication by smooth characters of ZP. Okay, by these characters of ZP, not the restriction of this representation to ZP. Okay. Okay. The main theorem. So the previous results are all implied by this main theorem by some what I call general principles and functional analysis. But this is the heart of the work. And it says the following: if we have an element alpha in the Grassmannian and a norm that is invariant under the Heisenberg group on the space of Schwarz functions and dominated by norm alpha, right? It's just a fancy way of saying that it's bounded from above by some constant times norm alpha, then this norm is a multiple of norm alpha. And so for example, we cannot have invariant norms strictly smaller than these norms alpha. Okay, next, I want to summarize the previous result, and also compare them to different situations where the field of coefficients are the complex numbers, or CL for L different than P. So when it comes to uniqueness of invariant norms, over the complex numbers and representation theory, we're usually interested in invariant unitary structures. And here there is a unique one up to a constant, just the ordinary one. And over CL, the sup norm is the unique invariant norm.
Yes, because we have R measure.
Right. Here, over CP, we don't have uniqueness of invariant norms, but we do have this special family of invariant norms, this norm alphas. Each is unique among the invariant norms below it. When it comes to the reducibility of the completions, then over the complex number, the L2 completion is topologically irreducible representation of the Heisenberg group. The completion by the sup norm over CL is strongly irreducible, and over CP, the completion by these norm alphas are also strongly irreducible. In all three cases, the smooth vectors in the completion are just the Schwarz functions. And when it comes to uniqueness of the topology of irreducible representations, Stone-von-Neumann type theorems, over L2, over the complex number L2, completion is the unique irreducible unitary representation with central character psi. Over CL, we have exactly the same statement. Over CP, we don't know. So we have this special family, but we don't know if there are any other. Okay. Okay, let me maybe discuss. Okay. So maybe in an attempt to construct new invariant norms, I mean, we don't have too many tools in our disposal. And well, we were very lucky to have these intertwining operators. But there is a very simple way to try to find new invariant norms, which eventually fails. but still gives rise to an interesting result. So let me consider norms of the following form. If you take a finite set I of the Grassmannian, I'll denote by norm I the maximum of these finite norms, or finite numbers of norms, norms alpha 1 up to norm alpha n. I will call such a norm small norm, or norm that are equivalent to it. And then, so here's the question. We can take this a finite set of norm alphas, take their maximum. This is a strictly larger invariant norm, and we can ask ourselves, are there any new norms underneath it? I mean, certainly norm alpha 1 is underneath it and norm alpha 2 is underneath it, but could we have something entirely new? And the answer is not. And actually, it is very, very strict. If we have a norm, an invariant norm, which is dominated by such a norm I, for a finite subset I, then there exists a subset J of I such that our norm is equivalent to norm J. So for example, if you started with the sup norm and the Fourier norm, they are very different norms. You take their maximum. This is a new norm strictly larger than the sup norm, strictly larger than the Fourier norm. But below the maximum of the sup norm and the Fourier norm, the only norms that you're going to see are just the sup norm and the Fourier norm. You won't even see a new norm alpha for another alpha. And a straightforward corollary of this, but important, says the following. If we have two subset I1 and I2, both finite disjoint subsets, and you consider the norm of I1, norm I1, and norm I2, then they are so different that there does not exist a semi-norm of the space of Schwarz functions, which is smaller than both of them. Okay, let me say a few words about the proofs. We use two types of methods. The first one is what I called general principles or functional analysis, and some of which are well known from classical functional analysis, such as the closed graph theorem and Bayes category theorem, some of which are more specialized to the p-Adic situation, which especially they are used to study this notion of strong irreducibility and related notions. Okay, so I won't read this line, it's just here so you can read it if you want. This is the kind of objects on which we apply this method from functional analysis. And the next kind of method that we are using is Q arithmetic in the space of continuous functions on ZP. So I won't have time to go over more deeply about what are these Q arithmetic is, but I just mentioned several things. So Q arithmetic or Q analogs are something very classical in mathematics and in physics, and they appear in many, many places. And they also appear in very recent and deep works, which I know nothing about. In our work, they are used as follows. They are used to, again, this is well known, it's a deformation for the usual Malloc basis of binomial functions. And this allows us to obtain a very, very large family of very good bases to the space of continuous functions on ZP, in which we can make some computations. Okay, so I'll skip this about Q analogs, and let me move to the final part of this talk. I would like to give a picture that summarizes this invariant norms and raise several open questions. Okay, so we'll work with the lowest dimension case, d is equal 1. The points in this picture are equivalence classes of invariant norms on the space of Schwarz functions. Here, up above, there is a point, there is a maximal equivalence class of invariant norms. We did not discuss this point, but its existence is nothing deep. This is also follows from some general principle. And here below, this is the Grassmannian. These are the norm alphas, parameterized by some nice geometric object, which in our case, where this one is just a projective line over QP. And here you can find the sup norm, and on the other side, the Fourier norm. Here, these are what I call the small norms. These norms that we get by taking maximum of finite numbers of this norm alpha. So for example, here you can see this norm I that's on the picture here is just the maximum of norm alpha 1, norm alpha 2, and norm alpha 3. And I should say that these lines that you see here are not real lines in any geometrical sense. They're just here to indicate that this norm is the maximum of the 3 points below. And this is the picture that we understand quite well, at least the bottom part. We understand quite well the completions by these norms and what other invariant norms lie underneath each point small norm. So for example, the rigidity theorem for norms alpha told us that we don't have any points below this projective line. There are no points underneath a norm alpha. And so in order to understand the full picture, we need to understand what points lies ahead of the small norms, above the small norms, and what points lies here on the side, if any. And so the first question that I want to ask, you can take this, instead of taking maximum of finite numbers of norms, you can take the supremum, say, of all of them. And the reason that the supremum exists, it's a finite number, is because the way that we chose this norm alpha in some uniform and normalized way. And so taking the supremum of all of them gives you a new invariant norm, which is larger than all these small norms. And now the question is this new norm, does it belong to the maximal equivalence class, or is it some new point in this picture here? If it is, in any case, we would also like to ask what happens more generally, taking the supremum over an infinite subset of the projective line, maybe not all of it. Again, this norm that we get is some invariant norm larger than all these small norms. Is it a new point or something that belongs to the maximal equivalence class? And finally, I'd like to mention the question that I personally find the most interesting. Do we have norms, invariant norms, which are not larger than any of the norm alpha, right? That in this picture should be here on the side. And this is one of these questions that answering it should be interesting regardless of the answer. Because if the answer is that such points do not exist, and any invariant norm is larger than some norm alpha, it will give us a very nice picture. For example, it would apply that the only reducible completions of the space of Schwarz functions are the completions by a norm alpha. And if, on the other hand, such norms do exist, then constructing them will be very interesting. And unless we missed something easy, it might require some new insights and new methods of constructing invariant norms. Okay, So thank you.